So hi everyone, I am Piradapan and today I'm presenting the paper named Target Localized and Cell-Based Image Analysis and Disease Diagnosis by Sanjis and Karim. This is from LMIL workshop at ICLR 2025. So this work proposed a new way to find and crop out the region of interest in biological image before doing detailed analysis. Next is the background and problem. So the image-based diagnosis is using the software and algorithm to analyze the image. So for example, the fluorescent microscopy image, they need the immediate cell profiling and phenotyping. And also colonoscopy image is also require accurate polyp segmentation. However, the target of interest, such as specific cell or regions, can be hard to detect um, because sometimes they may hide in the surrounding area or will even act like a camouflage against the background. The camouflage means the object is visibly hiding due to similarity with its background. So we have the deep learning that developing for the medical image segmentation, and this deep learning can handle many tasks. But these deep learning have a big drawback because they require they require large label dataset and heavy computational. This make them hard to deploy quickly in clinical setting. So we have great algorithm, but they are data and compute hungry. The core problem addressed by the author is how can we efficiently localize the target object in a biological image without rely on full deep model segmentation. So in the other words, can we like cheaply find where to look in the image so that downstream model can focus on that region. So let's look at the significance of the problem. So why does this matter? Like if we can isolate the region of interest, let's say a single cell or region, then any machine learning model only have to process much smaller image. So as the paper point out, reducing the searchable image area can minimize the training cost of deep learning method, and this will have two big implications. First is faster training and interference. Less input data mean less compute time. Second is less data requirement, so a smaller ROI might need fewer example or label to train a good model. So the in medical imaging, this is highly valuable. For example, in a resource limit like clinic, we might not have thousands of label image. If we can quickly discard the thing that we don't like a background, and zoom into the cell or lesion, and this can make a diagnostic algorithm work almost like a real time and with less annotation data. And the author also note that just as approach can lead to meaningful and cost efficiently representation of biological phenomena. So solving the problem can make automate diagnosis faster, cheaper, and more practical. Um, let's briefly review existing approach. The current state of art for medical imaging segmentation is rely on deep neural network like CNN. So previous work like Dong 2021 use CNN-based model for segmentation. They can achieve high accuracy and complex dual encoding and boundary aware loss, but they need large annotation datasets and heavy compute. Similarity to camouflage, the object detection method like CNET help with hard to see target, but it still rely on the deep learning. So overall, this method work well, but they are resourceful, and we need a motivate lighter training fee alternative. So the key gap is we need a lightweight processing step that directly find the region of interest before any heavy analysis is done. In other words, instead of feeding like a chunky large image into the neural net, can we find crop out on the small part where the target is, and then um, feed it in, so it's less time consuming. And there have been little work on combining classical imaging processing to pre-localize object in this way, but the other want to fill this need, and it's not aiming to replace segmentation. It's a tool to guide in by narrow down where to look. Now let's look how they do this. So the method is the pipeline method is they process the image using spectral and textural analysis to highlight the target, then draw a boundary circle around it. The core idea is to identify the target region automatically so that browsing tracks can be focused on the legend only. Here's a high-level rationale. So by converting the image to frequency domain, we can separate low frequency background and enhance high frequency edge. In parallel analysis local texture help pick out relevant region. So combining this, they form a mask of potential target area, and then finally finding a key point on that mask and fitting a circle, they get simple region of interest. So the author emphasize that this reduce the region should make later machine learning faster and more accurate. And then they state that a reduced searchable image area would minimize the training cost. So that rationale is smaller region, make it faster and cheaper learning. This guide focus is the main selling point of their method. And then let's look at the technical step now. The method consists of several image processing steps. So first, they compute the 2D FFT on the input image to get the magnitude and phase. Apply Gaussian high pass filter to the magnitude spectrum. This empathize edge. Also, they apply a root cubic normalize to further boost a bigger edge. And then they use the phase spectrum normalize to remove regular background pattern, and then regular structure tend to appear as strong phase information. So by normalizing this, they suppress the background out. And then they perform the inverse FFT using the filter magnitude and normalize the phase. The result is an image where the object is stand out and the background is slightly suppressed. Next is they do local entropy thresholding. They compute local entropy map of the inverse FFT image, often after a slight gradient burst. The area with high entropy often correspond to complex texture, like cell, then apply method to binarize the entropy image, yielding a binary mask or candidate region. So these steps produce a binary mask, highlight when they target like this. So next is area deduction. Multiply this mark with the original image, they zero out most of the background, leaving only reduced image around the target. And then they get to the neat circle of region of interest. They run free key point detection on the reduced image, find the distinctive point that often lie on the object boundary, and then they do convert hole and boundary circle. So among the fixed point, they shoot 30 lowest point and compute their convex hole. The center of this hole is taken at the center of the boundary circle, and the radius is set to reach the furthest of the point. So in the other words, they fit the smallest circle that enclose the important of the key point. So by doing this, the output is a circle centered on the target of the above step use of the shell image processing tick, and no train is needed. Let's look at the data and the result. The author tests the method on several biological image datasets. So 100 image in each dataset. They have the cell image dataset, have the colorectal polyps image 2 dataset, skin laser 2 dataset, and breast ultrasound 1 dataset. So the result is they got a high target retention. So look at the PSC2, they got really good number with 93.3% of the good truth marks, while using only 20.9% of the original image area. And then for the polyp example, for the culture polyp image, the boundary circle cover about 95% of each polyp area in 73% of the test image. Also the CVC colon, another polyp set got 85.5% of target, where retained with 59.2% area cap. And then also the lesions, the skin lesion got 73.0 retention with 46.2 area, and then the for breast tumor about 80% retention with 60.5 area. So in general, the method often retain most of the target while throwing away a large fraction of the image. The author also present qualitatively so. So they only their original image with the ground truth, which is red, and then their circle, which is in the white, and then the white circle is usually fit on the red region. So it means that overall the analysis claim the pipeline successfully they can localize object across this diverse image type. For the conclusion, the paper showed that the classical image processing pipeline can effectively local target in the cell, and medical image often retain 70 to 90% of the target area, while discuss much of the background. And for the advantage of this paper is a simple interpret table step where we got a lot of data set, no need for label training data, and focus region of interest is have potential to speed up downstream analysis. But they also have some limitation. So some GT is lost, like only 68% of GT retained in SKBR3, which is a large decrease. The boundary circle can be overlaid in a few cases, like the method assume a Rowley circle region of interest which may not fit for all the shape. However, a few criticisms come to mind. So first is the method is rely on many fixed choice. So like filter type, threshold, or the key point, it is not learned. So it may not adapt if image condition change. Like maybe the image have very noisy image, different contrast. Also the highlight output is only one boundary circle per image. So if they have like a multiple of the target, it might not get a good result. And then they also evaluate how much ground truth is inside a circle, but they do not show how this improve any real diagnostic tracks. For example, if we train a segmentation network on the clock image, would it actually learn faster or better? That was not tested yet on that paper. And then the sample size might be small, it need more diverse. For the future direction, the pipeline integration. So one next step is to integrate this method into the end-to-end process. For example, use the circle to crop the image and then feed it to the neural network. So we could measure if the training time and data is need actually drop and if the accuracy stay the same. And next is it still need to tuning the balance between area and the coverage, and finding the optimal number of key point or threshold could be automated. Third is extending to handle multiple target. Like I said before, it's only target one target, so multiple target might be good. Fourth one is the parts of the pipeline could be replaced or guided by learning. For example, increase or fix Gaussian and power transform. One could learn an optimal filter from data. Five is testing on more or various type of image like 3D scan, microscopy of different cell type, validate the approach robustness. Last one is since this method is claimed that there is a relative fast, no training needs, so it might be adapt for real-time use in clinic, perhaps on device during image acquisition. And that's all of this paper. Thank you so much for listening.